Hello everybody, it is Wednesday and again time for a new GIS and imagery analysis practicum. So this practicum is our sort of second round into the realm of imagery analysis, and if you were worried that we were getting away from GRASS and delving too deep into GIMP last time, your worries should be allayed, because this time we're going to get right back into GRASS and we're going to talk about multi-band imagery that is beyond the spectrums that we can typically see with our own eyes. So first things first, on the Blackboard site you can download a data set. This is project_4.zip. Just download it somewhere to your hard drive, and what's contained in this thing is a GRASS map set that should fit just fine under the same GRASS location that you were using for the Wadi Hassa. Now this is for Wadi Ziklab, it's north of there, but it's in the same UTM projection location. So just to refresh you how to do that, over here I've got my class GIS data project folder. Remember we talked about data management all those weeks ago. In this I have QGIS stuff that we were working on before. I have a folder for some exported, final maps, graphics, that kind of stuff. And here I have my GRASS database. This is what I point GRASS to when I start it up. Inside here I have all of my GRASS locations, and inside each of these I have map sets. So you're going to find the one that you were working in before for Wadi Hassa. If you recall, named mine Hassa WGS84 UTM Z36N. So I know that this is UTM Zone 36 North WGS84. I put Hassa because that's what we were working, but if it's data that's in the same UTM zone, it'll go in there just fine. And so here are my map sets, permanent, project 2 and project 3, and what I'll do is just extract my project 4, and what I'll do is find all of that in my this is my software to extract it from the zip file, and I'll just find this, and this is where I want to extract, so I'm just going to extract. And you see I have a new folder in there after it finishes up here, called project 4. Inside there I have cats, with a bunch of stuff in there, right? So there's a bunch of things in each one of these. So don't worry about any of this stuff. You don't have to get into this manually, but just so you know that it can go right in there, and then that's ready to go. So now, when I start GRASS, which I'm doing here, I navigate to my Wadi Hassa UTM Zone North location, because you see it's already pointed at my GRASS database. And now I see project 4. And it may be like grayed out here. That's fine. It's just because I was working in it before I zipped it up, and it has what they call a GIS lock file. It's not a big deal. You'll get this message. Just hit yes twice, and GRASS will start up. So what is inside the map set? Well, really it's one data set, but it's several data files. They're all raster data files, and these are data that come from a Landsat 7 tile of northern Jordan. And you'll see here there's several files in here. They have the same prefix, Jordan _ LS7, and then dot, and then they have a different number, 1, 2, 3, 4, 5, 6, 7, 8, right? So each of those numbers corresponds to a specific band of light, or set of bands of light that are recorded by the Landsat. So the first one to look at is this one, band 8 or dot 8. And we just click OK. We'll see a very detailed black and white image. Band 8 of the Landsat satellite is the panchromatic band. So this is typically exactly the width of light that we think of when we think of a typical black and white photograph, meaning it's all visible light from all the way red to all the way blue, but it's all condensed into one set of reflectance values, luminosity. So darker for things that don't reflect much across red, green, and blue, and lighter for things that do reflect a lot somewhere in the red, green, and blue. So if we zoom in, so this is the Dead Sea, by the way, what we're looking at right here. This here is the Mediterranean. All this black out here is just no data. This is where the tile ends. It's just coded black. And everything that's sort of some shade of gray here is land. So this little feature right here is the Jordan Valley, And Wadi Kuseba is right up here somewhere. So if we sort of zoom in on the northern part of the Jordan Valley, we actually see several features. We see kind of the Jordan River and the darker sort of vegetation. We see lightish stuff, which could be rocks and dirt, or maybe it's the city or something like that. And we see some darker areas up here. These might be tall mountains with trees or something growing on them. And if we go way up here towards the north, here we see, actually this is Wadi Ziklab right here. So I think Wadi Kuseva is just off the edge of the tile. But nevertheless, this is part of the region that we were looking at in that QuickBird image that we were looking at before, which was an RGB image, meaning a red, green, and blue, so we could really see the color. Here we have no color image in band 8. So if we zoom in pretty far, let's zoom in like that, we can see, yeah, some pretty good detail. We can keep zooming in, we can keep zooming in, and then we get to the point where things start to look kind of pixelated, right? So here's an interesting thing. Band 8 is 15 meter resolution. The other Landsat bands, however, are 30 meter resolution. So if I just go in here and I pick any one of the other ones, I'll pick band 1, which is actually the blue light spectrum. And I click here, you see the pixels are fatter, they're wider, because these are 30 meter pixels and the band 8 one are 15 meter pixels. So if you're getting confused already about this thing called the bands and all of this other stuff, I am going to be putting in Project 4 description, which I have yet to upload. I'm sorry for that. I will hopefully get to it tomorrow morning. A little table that will tell you something about the bands and the spectrum. Not only that, but some of the links that are in there in the Blackboard folder will take you to some really nice descriptions about Landsat data and the different bands and what wavelengths they are and what they're good for. So you're going to want to really read those things. They're not difficult to read. They have nice Landsat satellite pictures. But basically, this sort of table here will help you when we talk about combining the bands to make color images out of it, which is what we're going to do in today's practicum. So this little table right here is going to come in really handy, especially all of these numbers right here and in the order that they're in. So we're going to get to all of that right here real quick, but I just wanted to point out that you should definitely read, maybe pause the video and click those links. The one that says why are my trees red, right? And then also the one about Landsat, the different bands and what they actually are. So you want to read those things probably before continuing, because it will help you make sense of all the things I'm about to say about the different bands and the wavelengths and all of that kind of stuff. So first thing we're going to do, actually, before we do any analysis, we're going to load up, let's just have this band 1 loaded up here. We're going to zoom to that selected map, and we're going to right click on it, and we're going to go set computational region from selected maps. Now the region, remember, is important in GRASS, because if you're not careful about your region settings, you could do some operations and it'll be limiting it to a different part of the world. So since we are way down south, way off the bottom of my computer screen in Wadi Hassa, several hundred miles to the south, and if your region was still set to Wadi Hassa and you start to do some things, you're going to get real frustrated because nothing's going to happen up here in northern Jordan, north of the Dead Sea, right? Actually, Wadi Hassa is somewhere right down in here, right off the bottom of this map plane. So what you need to do, first thing first, is to set the project region boundaries to just, in this particular map set, move the focus up here to the same extent as this. This also sets the resolution to 30 meters, because this particular tile is a 30 meter tile. If we set the region to band 8, it would have set it to 15 meters, which we are going to do in a little bit, but we're going to start off at 30 meters because we're going to work with the whole Landsat tile, and depending on the speed of your computer, it might take you a little while. So just make sure you set the region, like I said, to match this whole area, and we will be fine. Okay, so let's talk about the spectral reflectances that are captured by Landsat satellites, and let's talk about how we can use that to our favor. So Landsat 7, Landsat 8 is the latest one. We're not going to deal with that because it's got some more complicated things. Landsat 7 is a fairly modern sensor. It captures 8 different kinds of light. We already talked about band 8, which is the panchromatic band. But let's talk about all of these other bands that we have here. 1, 2, 3, 4, 5, 6, 7, and 8. And actually, to do this, I'm actually going to open up that web page just to show you very quickly. Hopefully my poor little computer here is not going to be overtaxed recording the video and grass and trying to open Firefox at the same time. Okay, here we are. So let's crud. Sorry about that. I always forget if you close the last tab, it also closes Firefox. So that's a little tip to you people who like to use Firefox as your main browser. Don't close the last tab if you're trying to do something. Alright, here we are again. Okay, so now let me put into the search box Landsat bands before it loads my email up. Alright, so here we have Landsat bands. Alright, band designation for the Landsat. You see, I've clicked this link before. I'm doing my research for you special people. Okay, here we go. So it's got information for all the different Landsat missions. We're going to scroll down to find the one that says Landsat 7, and here we go, right? Band 1 is blue light. It tells you even the wavelength of the light in micrometers and the spatial resolution, 30 meters. Band 2 is green light. Band 3 is red light. Band 4 is near infrared, or NIR. Band 5 is shortwave infrared, or SWIR, sometimes called SWIR 1. Band 6 is thermal, which is also a kind of infrared. Band 7 is a different wavelength of shortwave infrared. And band 8 is the panchromatic. So it's kind of confusing to have the sort of thermal inserted here because it's actually the longest wavelength. It should be, technically, if we're going from shortest wavelength to longest wavelength, the thermal band should come after 7, and the panchromatic band should be, it's actually the combination of 1, 2, and 3. So if you look at it over here, it's 52 to 90, which is actually technically just the green, red, and near infrared reflectances for this particular Landsat mission. So this is cool, right? So we're seeing some interesting combinations already in our head. Like we can definitely do red, green, and blue to see what we can see, but we can do some other combinations of these things, what we call false color satellite images, that will make some different surface patterns more clear to us. And if we look at my little table, which I'll put in there, we'll see actually if we want to make certain features like agriculture or have vegetation or urban areas or whatever, there are specific combinations of these wavelengths of light that are going to really make those kind of features pop. Alright? So I'm going to close that so I don't crash my poor little computer. And I'm going to go back over here. And so if we load any one of these bands up, it doesn't matter which one we pick, let's just pick 3. It's going to look like black and white in grass immediately, because technically each band is black and white, meaning it's just the reflectance values in that segment of wavelengths. What we need to do is combine several bands into a red, a green, and a blue channel, and let the reflectances that we are seeing in black and white be shown in pure red, pure blue, and pure green. And when they kind of overlap with each other, we'll actually get the impression of a color image. And there are a couple of different ways to do this in grass. The easiest way is to go here, not the normal one that we click Add Raster Map Layer, but the one next to it where we're adding the shaded relief. But in this case, we're going to pick an Add Rgb Map Layer. And you get this DRGB. And it tells you raster map to be used for reds, map to be used for greens, and raster map to be used for blues. So if we pull that down, let's just do our standard red, green, blue visible light bands. So we know band 3 is the red band, so we pick that for reds. Band 2 is the blue band, so we picked that for, I'm sorry, it's the green band, so we picked that for green. And band 1 is the blue band, so we picked that here. We just click OK. And now we're starting to get a sort of color image over here. And we can zoom in on it and see that it's sort of color. It's sort of washed out though. And this is because the Landsat sensor is not the same as a camera sensor, as a typical digital camera sensor. It's actually trying to fit a wide dynamic range of values in the color space or in the reflectance space. And so just off the top it's going to look pretty washed out. We have to manipulate some of these things, their reflectances a little bit, to make it pop a little bit. So if I zoom back out to the entire image right here, we'll see what that means. And lucky for us, there are some tools here in Grass to do that. And we're going to go to the Imagery Tool Tab. This is one we haven't actually seen. We spent a lot of time over here in raster and vector. But the Imagery Tool Tab is definitely something that we're going to want to learn about. So what we're going to do here is go to the let's see, Manage Image Colors and Color Balance for RGB, i.colors.enhance. And this is going to be cool because it's going to let us kind of apply an automatic histogram stretch to each of these individual bands, right? So we'll pick our red channel 3, our green channel 2, and our blue channel 1. And we'll go to the Colors tab here, and we'll just check the second box that says Preserve Relative Colors, but adjust their brightnesses. So we hit Run. It's going to take a little bit of time because we're doing it on the entire map. And my little laptop here again is not the fastest laptop in the in the face of the planet. Okay, so there we go. And now we come back over here and we redisplay these things. Now we're talking. We're definitely seeing a vast improvement over before. Now you can play around with some of these other checkboxes. They won't do a huge amount. If you want to go back to the way it was, you can check this one. This is a different kind of histogram stretch. It doesn't tend to work as well in my experience. So I recommend using this one first and then maybe playing around later to see how the other sort of options work. But you can see right here we have basically a much more natural looking image. So that's really, really great. What we can do now is actually mess around with some of those other bandwidths of light. And if we look at the little table that I'm going to give you, you'll get some clues as to what to do. So what we've done is actually this natural color image, band 3, 2, 1 in the red, green, and blue slot. So that's what we just did. Let's go to this one right here, which is the next sort of natural combination of colors. We're going to start getting into false colors. So what we're going to do here is do the same RGB kind of image, but instead of the red, green, and blue going in those slots, we're going to put the near infrared, the red, and the green. And we'll see what that actually looks like. So let's go back up here. So this is my red slot, and I'm going to pick band 4, which is my near infrared. This is my green slot, so I'm going to pick red, band 3. And this is my blue slot, I'm going to pick green. I'm going to click OK. And all of a sudden, we get a totally different image over here. Now we may have to go back into this iColors Enhance and redo our enhancements using those bands in the right, red, green, and blue channel. So now we're going to put 4, and then I'm going to put 3 in the green channel, I'm going to put 2 in the blue channel, I'm going to hit Run. And again, on my little tiny laptop, it's going to take a little while. And we're waiting, and we're waiting. And there we go. And now we can hit redisplay, and there we go. We got less of a blue tint to it. That was because our infrared band hadn't been optimized. But now you're seeing a lot of red, right? So that's really kind of interesting. Remember, we put infrared in the red band. So anything that shows up brightly red in this image here is actually not red light, but infrared light. Okay, so it's going to take a little while for that to sink in, I think, for some of you. But if we zoom in on any of these things, we'll actually see that things that should have been green are bright red. So this is what it looks like with our new band combination, infrared, red, and green. If we go back to our previous arrangement, so I'll just put things back, 3, 2, and 1, and hit apply, we'll actually see things that are green still a little bit washed out, but things that are green on this showed up bright red in the other one, and actually makes lush green vegetation really pop out, especially irrigated farm fields. So this combination of infrared, band 4, red, band 3, and green, band 2, is really useful for making vegetation pop. Now, it's not the only combination of bands that can make certain vegetation pop. Here we can take our same infrared, we can put our shortwave infrared, our first shortwave infrared, in the green zone, and we can actually put blue in the blue zone. So let's do that. So we'll leave our infrared alone here in the red band, and this band will go up to 5, our shortwave, and the blue band will actually pick blue. We'll hit apply, and we'll see, a slightly different color combination. Here we have still irrigated farm fields showing up in red because the infrared is still in the red band, but this purple is also showing up other kinds of factors. So if we look over here, we go blue and red make purple. So so that's a combination of vegetation and blue light, whatever that means. And if we look for anything that might be green, whoops, sorry about that, which probably not going to be that many things. Okay, I need to recenter there we go. Yeah, it's mostly going to be purple and red, and we have a few things that are green, which are reflecting in that shortwave band sort of on their own. Let's take a look at some other combinations that we could do. I think rather than the 4-5-1, the 5-4-1 might have been the one that I was trying to actually show you. So let me try that again. 5 in the red, infrared in the green, and then 1 we leave like that. Yeah, so this one's going to be real green, right? So now we have green looking like, well, the vegetation that it is. So same kind of bands, but we're just shifting where they show up in the colors, and they help us see things slightly differently, right? Yeah, so if we just go up to the northern Jordan Valley where they have a lot of agriculture, you really see some of this stuff right here. And we can zoom in even more. We can really see how some of these color patterns are starting to pop, right? Alright, so there are several other combinations that you can do. I encourage you to play around with that. 5-4-3 is another common band combination for vegetation analysis. We'll just hit OK on that one, and we'll see. It's very similar, but we get slightly different hues, right? And if we zoom out a little bit, we can see basically the different bandwidths are good for different things. Urban and sort of bare earth areas or rock can be made to pop. Vegetation can be made to pop. Roads can be made to pop. Water can be made to pop. And so you'll use that sort of as a guide as well as the readings over there. So that's going to be part of Project 4. And another part of Project 4 is going to be doing Pansharpening and then a special index for studying about vegetation. So firstly we're going to do is the Vegetation Index, the Normalized Difference Vegetation Index. And what this is simply the difference between the infrared band of light and the red band of light divided by the addition of the infrared band of light and the red band of light. And if that's confusing you and you're thinking, oh man, I got to use MapCalc to do that, don't worry. They've made it simple for you here in GRASS. In fact, all you have to do is to go down to Satellite Image Tools and find, Satellite Image Products, and find Vegetation Indices, I.vi. And I'm going to show you quickly the manual page for this thing. There's all kinds of combinations, statistical combinations of these bands, and they have all these funny acronyms, so all of these things that you can do. And they're good for different things. Like, so if the false color images are good for different things, then these are all good for other different things as well. The most common one is the NDVI, which is this one right here, Normalized Difference Vegetation Index, because it tells us something about the health of the vegetation that's growing, which actually can tell us something about what's underneath the surface. Something is constricting water flow or enhancing nutrients will make vegetation pop, right? And we scroll down a little bit over here, it tells you how each one of these things is calculated. And if we find our NDVI, we see it tells you exactly what I said. NDVI equals near infrared minus red divided by near infrared plus red. So it's pretty simple mathematically, better than something like this for the MSAVI, which is for Modified Soil Adjusted Vegetation Index, or the MSAVI2, or some of these other more complicated ones. I'm giving you a nice simple one that's also a really common one that is useful. And not only that, it tells us what the bands are of our Landsat TM version 7, right? Telling us 4 and 3 are the bands that we need to play with to get this done. So if we go back up to the required tab, it's always going to ask for the red on the first required tab. So we're going to find band 3 right here. We're going to call our output, well, I'll call it North Jordan NJ underscore NDVI. We're going to leave this as NDVI. This is where you'd select all your different ones that you wanted to do. And then the optional inputs, depending on which vegetation index, you might have to put more than 2 channels. That's why these are all optional. For us, for NDVI, we just need to find the near infrared, which is band 4, right? So we put band 3 here, we put band 4 here, and that's basically it. We just hit run. And we let it chug away. Where did it get to? Sorry. So it may take a while on your computer if your computer is slow, like my little laptop here. On the computers in the lab, this will go quite a bit faster. And we're almost there. Halfway. I'm going to zoom back out. There we go. And so we'll see. We're doing this again for basically all of northern Jordan, so it's a lot for my little computer to handle. If this is trouble for you, you can definitely zoom in on a part and reset your computational region. And we're going to do that before we do the Pansharpening, because that's really quite computationally intensive. Okay, so it's getting close. Real close. There we go. Okay, so the first thing you're going to say is, what the heck does that look like? This is a special color scheme for the NDVI, and the greener it is, the healthier the vegetation. The whiter it is, the least healthy the vegetation. This is a special color rules. So if I was just to go over here and go to my set color table and go to my define and look at my color rules, if you go down, you'll actually see one called NDVI right here. And basically you've got water in the blues, unhealthy in the whites and the browns, and then the darker green it is, the healthier it is. So it's going to look weird, right? And let's zoom in on a little area just to make it more plain. So we'll zoom in on this area right here. It's going to look strange at first. If we put a legend on this, we can actually see, when we move it around over here to where we can see it, there's actually a value of 1, which is perfectly healthy vegetation, and 0, which is no vegetation, and then things in the minus are actually water. Alright, so it calculates all this for us. It normalizes it from 1 to 0, or actually 1 to minus 1. And that's why the normalized difference vegetation index is really useful. We know anything close to 1 is really healthy, growing vegetation. Anything close to 0 is, well, non-existent, dead vegetation, pretty much. There's other things that may have reflectance values that go to this, but this is pretty good indication of the health of different vegetations. And so if we zoom in to one of these agricultural areas here in Israel, we can really see fallow fields with nothing growing on them, bare land, and then lush irrigated fields, and then fields maybe that have just recently been cleared or that are sort of dying off in time for harvest. And then we can actually see some more natural style vegetation that's less affected by some of these irrigation patterns. So it's really useful for us to see some of those vegetation health status indicators. Our Landsat data is 30 meters, so we're not seeing a lot of subsurface things pop out, but we certainly could. For example, if you fly a drone, sometimes they have a special NDVI camera that only takes red and near infrared light. In fact, I have one of those cameras for our drone that we're getting for the class. And so you can make this at a much finer spatial resolution, and you could see how a little micro variation in the health of the vegetation might indicate what's growing below the surface. So you'll have to make an NDVI. It's pretty simple. And then you'll zoom into an area and you'll talk about the patterning that you see, talk about the lushness of the vegetation. The final thing that we can do, so you're going to do false color images with different band combinations to help make some features pop. You're going to make an NDVI. The last thing you're going to do is Pansharpening. So what I'm going to do is set my computational region from display, because I'm only going to want to Pansharpen this area. So this is perfectly fine. In fact, you could have zoomed in and set the computational region to match. But you're going to need to make the region resolution 15 meters. And there's a couple ways you can do this. The easiest way at this point, after having zoomed in, set the boundary to the display, go back to settings, go to region, settings, region, set region, g.region, and find the resolution tab. And here where it says 2D grid resolution, change that to 15 and hit run. Okay, so now if we print our resolution, print the current region, we see that we are 15 meter resolution right here, and we have our north, south, east bounds set to this window that we were looking at before. So what we're going to do with Pansharpening is we're going to take this panchromatic band, which has reflectances that run the gamut, in our case here, across the visible and the near infrared bands of light, and it does it at a finer spatial resolution of 15 meters. We're going to take those reflectances that are gathered at 15 meters and use them to update our 30 meter resolution data by basically statistically matching the patterns at the coarser resolution to those at the finer resolution. And because we actually have data at the finer resolution, when we statistically overlay the two, we have something to interpolate from, something to base our fining up of our coarser data on. And we're basically going to be able to turn our 30 meter data into 15 meter data that in a way that's not making it up through a just total interpolation. It's actually based on a known set of data. So it isn't the same thing as capturing all of those things at 15 meters, but it's pretty close to it. In fact, it's the next best thing. Pansharpening is also made pretty easily for you. You don't have to use the map calculator or anything. You just have to go back to the Imagery tab and go to the Pansharpening tab, i.pansharpen. And it's going to ask you first of all, the map to be used for red, green, and blue. I suggest doing the visible light, red, green, and blue, but also eventually doing probably your near infrared as well. And this could also be the first step before you do any of the other things. You can zoom in like this, set your resolution and all that stuff to match a zoomed in area, and then do a Pansharpening on the bands that you want to manipulate, and then you can do all of this at a slightly finer resolution. Mainly what I want you to do this part for is to see how you can actually increase resolution of the Landsat data to 15 meters for your little project area that you're working in. Finally here, you got to pick band 8 for the high resolution panchromatic band. And here, it's going to ask you a base name, and I do P sharp. And then it'll add that as a prefix to everything. And leave the method as IHS. The other ones, there's two other ones in here. They might work okay for some situations, but IHS is sort of the best method for us at this particular moment. And that's really all you have to do. There's no options or anything. You have to click. Again, make sure you're zoomed in. Make sure you set your resolution to 15 and your region boundaries to a small area, because if you try and do this on all of northern Jordan, it is going to take quite some time. It's going to take several steps, and I'll tell you what it's doing up here. And there we go. Okay. So we've pan sharpened these things over here. What we're going to do is go back to our false color image, and we're going to add in now our, where is it? Rgb. We're going to add in now our pan sharpened red, our pan sharpened green, and our pan sharpened blue. Now, the reason why I had you do this last is because it just changes all the little prefixes to red, green, and blue, regardless of what band you actually put in there. So if you put infrared in for the red band, when you do pan sharpen, it's going to call it P-sharp red. So that's why I'm sort of doing this at the end for your sort of last final pan sharpened RGB. If we hit apply, oh, it looks crazy. It looks all weird, right? Well, remember, we got to fix the colors. Okay, so we got to go back to our eye color enhance, and we have to now pick our pan sharpen bands: P sharp red, P sharp green, and P sharp blue. And hit run. There we go. We hit reload. Okay. And it's still going to look a little strange, but that's okay. So the pan sharpening will mess with some of the reflectance values. Here's where you might need to hit some of these other things, like extend the color space. And that might make it too dark. Preserve relative colors. And we redo this again. It's still too dark. The other thing that we can do is actually to go to our raster, manage colors, and go to our colors that we're used to seeing. We can actually grab our individual bands here, and we can give them where are they? Here they are, different gray stretches. So we can give them the gray dot equalized stretch, and we have to go through each one: the red, the green, and the blue. And it may adjust the colors there. That's sort of what the eye colors enhance is doing. So if that didn't work real well, we can go back to our regular gray, and we can try a different kind of histogram stretch on it. No, that didn't change anything. Or we could try, well, the logistic one won't, logarithmic one won't do it. Try gray 1.0. The histogram stretch doesn't do anything. So that's kind of the best we're going to get at this particular output. Mainly the blue channel looks to be like overpowering things for us here. And I wonder if I accidentally put them in the wrong slots when I did eye pan sharpen. So I picked 3, 2, 1. No, I did that fine. Well, that's kind of interesting that the colors are all kind of washed out. It typically doesn't do that, but apparently did that for us here. So yeah, that's basically all I wanted to show you for this week. We're going to do some more stuff in GRASS next week, including automatic classification. So just to recap here at the end, the different band combinations for showing you different features, vegetation versus soil, Ndvi, which is a standardized vegetation index having to do with the health of the vegetation, and then pan sharpening, increasing the resolution of different bands that were taken at 30 by using the 15-meter band to help statistically improve their spatial resolution. Alright, that's all I have for you tonight. See you tomorrow.